Electric motors have been part of the motor vehicle since the first batteries were installed. Traditionally, just for starting the engine, we're now seeing them as part of nearly every vehicle system. Whether used for opening a window, operating the throttle, or propelling the car, it pays to know how an electric motor works. The physical design of the motor will change depending on its power source, either alternating or direct current. Although either type still uses the basic principles of electromagnetism. A motor converts electrical energy to mechanical energy using opposing magnetic forces. Most DC motors use either a permanent or electromagnet as the field, and an electromagnet as the rotating member. In its simplest form, the DC motor uses the magnetic principles of opposites attract and like forces repel. The armature by itself is just a length of insulated copper wire wrapped around a shaft, with each end terminating at a pair of contacts. When we connect a voltage source to the armature contacts, current flows in one end of the copper wire and out the other, completing the circuit. This flow of current causes the formation of magnetic flux around the armature. If we increase the current flow, the magnetic flux intensity will also increase. This is a basic electromagnet. By placing two opposing stationary field magnets around the armature, we have created the beginnings of an electric motor. The polarity of the first field magnet acts against the armature magnetic flux, forcing it away. As the armature turns through 90 degrees, the second field magnet attracts the winding. From this point, our source voltage contacts, or brush set, has reached the break in the armature contacts, or commutator. The electromagnet is momentarily switched off as the brush set slides over the gap in the commutator. Momentum of the armature continues the rotation of the commutator until the wire has turned a full 180 degrees. Now we can observe that both parts of the commutator are now touching the brushes, although in a reverse position. Current flows through the copper wire once again, creating a new magnetic flux around the armature, only to be pushed and pulled away from the field magnets. A working electric motor uses many individual commutator segments, which provide a near seamless turning effort, as each segment in turn is energised. The insulated copper wire is wound around a soft iron core that intensifies and directs the magnetic flux, and adds some mass to the armature, aiding in momentum once turning. The rotating armature requires an electrical connection to the voltage source through a set of low friction contacts, or brushes. These brushes are commonly made of a carbon graphite compound. The ends of the shaft must be mounted in a bearing or bush, allowing the armature to rotate easily. Increasing, decreasing, or even reversing the current flow through the armature will have a corresponding effect on the shaft rotation. Most DC electric motors are designed to rotate and produce peak torque in one direction only. The motor will operate in reverse, but with a lower RPM and torque output. The manner in which the armature is wound is the main contributing factor to direction and torque produced in the motor. A lap-wound armature has opposing ends of the copper winding placed 180 degrees apart. These are the most common type of DC motor, as they produce a reasonable level of torque and reasonable rotation speeds. A wave-wound armature has opposing ends of each winding placed either 90 or 180 degrees apart. This allows a second set of brushes to be added to the armature circuit. With two circuits operating simultaneously, torque output is also increased. Using this method requires the use of additional field magnets placed around the armature. Using permanent magnets for the field poles is a cheap alternative to using electromagnets. An electric motor using wound field coils is able to produce greater levels of torque with a longer service life. Field coils may be used in an electric motor to increase the torque output or regulate the rotational speed. These coils take the place of the permanent magnets and produce the necessary magnetic flux to cause armature rotation only when connected to a current source. The field coils may be connected in several different ways. A series wound electric motor has the field coils connected in series with the armature winding. All current supplied to the motor flows through the field coils and armature, creating the strongest magnetic flux possible. This means the armature will turn at maximum revolutions shortly after startup. This is not an ideal property for longevity or reliability of the motor. Although series motors develop maximum torque on initial start, as the speed of the motor increases, the torque output decreases. This is a result of counter-electromagnetic force caused by self-induction. As the armature turns, its windings cut through the magnetic flux from the field coils, inducing current back into these same windings. The induced current opposes the normal current flow from the voltage source, thereby reducing the strength of the magnetic flux. The faster the rotation of the armature, the more current is induced in the windings, therefore reducing the torque output of the motor. Series wound motors are generally designed for engine starting, due to the high torque available at low revolutions and the short run time of these motors. Current from the voltage source flows through the field windings then to one side of the commutator, with the ground circuit supplied via the other brush. This design may incorporate multiple field poles and a corresponding number of brushes. A shunt type DC motor has the field windings connected in parallel with the brush set. These motors do not decrease torque as the armature speed increases. This is because the induced current, or CEMF, produced from the rotating armature does not affect the parallel connection of the field coils. Shunt wound motors are the most common type used in automotive applications, as they have a limited top rotational speed due to their parallel connection, making them reliable and durable. A compound or series parallel motor is an amalgamation of both types, benefiting from high starting torque output and limited rotation speed. One field coil is connected in series with the brush set, while the other is connected in parallel. The field coil that is shunt connected is used to limit the speed of the armature. Compound motors are generally used for starter assemblies in motor vehicles. With the demand for more hybrid and electric vehicles now upon us, it's probably a good time to brush up on electric motors. Thanks for watching.